Good afternoon, everyone. So I'm here to talk to you about some of the work we're doing at NC State on high-throughput radiation detector systems. So by way of background, what's motivating us is that, as you're aware, analog to digital conversion is advancing very rapidly in terms of its resolution and its sampling rate and its channel density, all of which are increasing, and its cost, which is rapidly decreasing. And so our ability to digitize signals is rapidly surpassing our ability to analyze them in near real time. Furthermore, there are many multimodal radiation measurement systems that are under development by NNSA and some other agencies that include things like gamma and neutron time of arrival and energy and multiplicity systems. In other words, systems that can measure all of these parameters simultaneously. Examples of those include fast neutron imagers as well as gamma spectroscopic imagers. And some of them can output hundreds of gigabytes to terabytes in a single short measurement. So what the group I work with at NC State is doing is working with three different partners, Sandia National Labs, Oak Ridge National Lab, and Duke University, to develop some alternative methods for data compression and analysis in examples of high throughput radiation detection systems. So I'll just start by describing each one of those projects. The first one is a collaboration with Sandia National Labs on their single volume scatter camera. So just a reminder, scatter cameras basically exploit the kinematics of scatter to reconstruct the incoming direction of the particle to within a cone, and the superposition of many cones coincident with each other identifies the location of the source in 4 pi, so they're great for identifying where a source is over long range in 4 pi. Normally they're made with multiple scintillator volumes that have space in between them, and the problem is a lot of times that the neutron or gamma ray that strikes the first surface, the front plane, does not also strike the back, and so they suffer from fairly low efficiency. You can potentially make a single contiguous volume scatter camera by taking advantage of advances in pixelated high-speed photodetectors like microchannel plates. This is an idea that Sandia forwarded about 3 years ago through an LDRD. And what they showed was that if they could attain about 1 to 2 centimeters resolution between sequential scatters, they ought to be able to improve efficiency over a multi-volume design by about a factor of 10. The problem is that these microchannel plate detectors have lots of pixels, typically either 64 on a small 5 centimeter by 5 centimeter detector, or as many as 1024 on a single photodetector. And in order to reconstruct where the scintillations occurred in that three-dimensional volume of the scintillator, you end up having to analyze, fully digitize every pixel at high speed. And that turns out, just the volume of data that you have to acquire turns out to be one of the most significant challenges to building a single volume scatter camera. So when we first started working with Sandia, actually at SORMA here in Michigan, what was that, 4 years ago now? Yeah. I suggested to the PI at Sandia that there might be an alternative design that would reduce the requirement for high throughput data acquisition. The idea was basically to take that single volume and to optically segment it into channels. Each one of those scintillator channels is segmented from the other, so light that's created in one channel remains in that channel. You could replace a large number of digitizers required by the optically contiguous design with a large number of discriminators, which are generally much lower in cost. And you would only need to digitize two photodetector channels, in other words, on either end of the scintillator channel for each interaction. So you have a great reduction in the data you'd have to acquire. So the XY location of the scintillation is easy. You identify it by the channel that collected the light. Determining the Z location is actually pretty challenging. So this is a JON4 simulation shown in the upper right-hand side of what the photoelectron time of arrival history would look like for a typical energy deposition of 1 MeV inside a scintillator channel that's 20 centimeters long by 1 centimeter by 1 centimeter. So not big, but not tiny either. So if you look at quenching, 1 MeV results in 150 keV of energy deposition. The luminosity means you're going to get about 1,500 scintillation photons. And a channel of those dimensions, your light collection efficiency is about 30%. So what that means is that on either end of the channel, you only get about 100 photoelectrons after you take into account the quantum efficiency of the photocathode. So that has an uncertainty of 10% associated with it. And if you attempt to take the ratio of those two responses, you end up with 15% uncertainty, which doesn't sound that big, but basically if you look at the histogram of the ratio of light collected on either end, yeah, the means are separable, but the tails overlap significantly, and you end up, for the dimensions of the channel that I described, only being able to figure out where the scintillation occurred to within about 5 centimeters, which won't cut it. So what we did was to use Geon4 to model the optical photon transport inside the channel and come up with a response function for the channel as a function of scintillation position, and then fit that response function to the photoelectron arrival time history. So that represents the best estimate of where the scintillation occurred. That produces a much more precise estimate of where the scintillation occurred, and I'm showing on the bottom right basically a plot of the actual position versus the estimated position. And for 1 MeV of energy deposition, you can locate the scintillation to within about a centimeter, and for 2 MeV of energy deposition, about 5 millimeters. So we then took that response and used MCMPX Ptolemy to model how the thing would be able to image a point source of fission neutrons. And so there is a comparison on the right between a simple back projected image and then a image that's been reconstructed by maximum likelihood estimation. And so you can see you can reconstruct the point source location in 4π fairly precisely. So I did not recognize until lunch that I was going to be right after Pete, so some of this is going to be a bit repetitive of what the students just described. But the other system that we've been working with is Oak Ridge and Sandia's neutron-coated aperture imager. We deployed that with them to the DAF in 2015 and 2016. As Pete mentioned, there are 1,600 physical pixels. So besides recording the pixel number in each channel, you also record the particle type, the energy deposition, and the time of arrival. So it's a gigantic data cube. We conducted images of weapons-grade plutonium and highly enriched uranium. As Pete showed, we have developed different techniques to reconstruct images of fissile material. He went through this pretty quickly because he had to talk with a couple of other guys, so I'm going to describe this just briefly. The way to exploit the fission reaction chain dynamics is really to look at the relationship between energy deposited and time of flight, all right? So if you say that a fission occurs at time 0, and I'll explain how we mark time 0 in a second, you'll observe a neutron count sometime later, and almost all of the time the energy deposited will be less than the apparent kinetic energy by the time of flight that you measured. Sometimes, however, the neutron will arrive later than you would expect based upon its energy deposition. In other words, it appears to deposit more energy than its kinetic energy. That, of course, is impossible. It's just indicating that your measurement of the flight time is wrong because there was an intermediate fission event. So the way you measure when the fission occurred is you go back from the neutron count and you find the preceding gamma ray count, and you take the time difference between the two to measure the time of flight. So if you build up a histogram of apparent time of flight versus energy deposition, you can divide it into two parts. One which will come primarily from fission chain reaction neutrons, and that's in the upper right-hand side. So the image on the top right over here shows the reconstruction using all of the neutrons, and this image shows the reconstruction using only the neutrons that we think come from fission chain reactions. So it eliminates the Californium source that's visible at the bottom of the image. It only shows that this material is fissile, not just fissioning. Then also we performed some active neutron measurements of highly enriched uranium using a DT generator. So basically by analyzing the response of the imager only after the DT pulse was over, we were able to reconstruct an image that contained only the target, which in this case was 13 kilograms of highly enriched uranium. By the way, in terms of the plug, tomorrow at lunch, 12:30, we're going to have a brief discussion of possible measurements for next year's campaign at DAF, and anyone who's interested is invited to come talk. So the last collaboration we have is with Duke University. We're also soliciting people to come up with better acronyms for this experiment. But we've been calling it a creeper. The idea really is to use the kinematics of elastic neutron scatter to do a very precise, very comprehensive characterization of anisotropy and still beam. Now, we're familiar with Patricia Schuster's work, and a lot of the other work has been done on it. The difference here is that we're able to, by using kinematics of scatter, measure multiple proton recoil energies simultaneously for a single beam exposure. What allows you to do that is essentially we have a DDN reaction creating a neutron beam that's essentially monoenergetic in the forward direction, striking the target detector composed of still beam, and by measuring which one of these backing detectors that fired, we know the scatter angle. If you know the neutron energy and the scatter angle, then you know the proton recoil energy. And it turns out you can actually measure it fairly precisely that way. Furthermore, on a single beam energy, we can measure multiple proton recoil energies between 500 keV and 10 MeV. So as I pointed out, we know the neutron beam energy, we know the scatter angle within a few percent. We can estimate the mean proton recoil energy to within less than 1% with about 24 hours of beam time. And by looking at the relationship between light output and time of flight in those backing detectors, we can see these are all the single hydrogen scatter neutrons. These are multiple scatter neutrons. And then this is actually DD breakup. We're able to essentially discriminate out all of those nuisance events that would contribute to the uncertainty in the measurement. And so using those experiments, we've been able to do an initial characterization of still beam anisotropy about the C prime axis. That's the one that's perpendicular to the hexagonal plane. I know the first time you look at this, it's a little hard to interpret. That still beam detector was on a rotation stage. So what you're seeing is the still beam being rotated in the neutron beam. And you see that you have a repeating structure every 60 degrees because you're rotating the hexagonal axes through that beam. And what we see is that when the C prime axis is parallel to the beam, we get the minimum light output. When it's perpendicular to the beam, we get the maximum light output, which is comparable to observations that have been made before. So the problem with that is that single plane of backing detectors doesn't allow us to measure the azimuthal angle. Tunnel, because it's an old low energy physics program, they actually have a lot of great stuff lying around, including a cache of about 300 plastic scintillators, including the photomultiplier tubes. So the proposal that we're working on with them is to essentially expand this measurement to use up to 300 backing detectors so that we can measure the azimuth and the polar angle at the same time. How am I doing on time? Okay, great. So the problem is we can't afford to digitize 300 backing detectors. We can't even afford to buy discriminators for 300 backing detectors. So what we're working on, and one of my students has a poster on it, is to use, I'm going to describe it as a series RLC circuit. That's the very naive description. It actually ends up being a little bit more complicated. But essentially, it's a damped oscillator. Right? So if you run the detector signal, the anode pulse that we're all accustomed to seeing, through that oscillatory circuit, you get a signal that looks very much like this. This is a real measurement here. And so we can tune that oscillator so that each detector oscillates at its own characteristic frequency. So by analyzing the frequency content of that signal, we know which detector fired. Okay? That means we can multiplex multiple detectors into a single digitized channel, analyze it in the Fourier domain, and say it was detector number 5 that triggered because it's oscillating at 5 megahertz. So that's good. It allows you to do coincidence with a large number of detectors with only a small number of digitizer channels. But we wanted to see if you could do something more. So in theory, the energy collected, in other words, the area under the input pulse, ought to be encoded in the amplitude of that oscillatory pulse. Furthermore, the time of arrival of that pulse ought to affect the phase of that oscillatory pulse. And so what I'm showing here is the charge collected on the vertical axis versus the amplitude of the oscillatory pulse. So this is energy. And then the phase over frequency on the horizontal axis versus the zero crossing time for a constant fraction discriminator. So that's timing. So basically, using those same oscillatory signals that we can multiplex into a single digitizer channel, we can actually also estimate relatively precisely the energy deposited and the time of arrival. So just to summarize, we're working with Oak Ridge, Santee, and Duke to develop some alternative approaches for data analysis to try to work with I'll call them high data velocity systems. In other words, systems that collect a lot of data of high dimensionality very rapidly. With Sandia, we're working on the single volume scatter camera constructed from pillars of plastic scintillator that should be able to reduce the number of digitizer signals we need by a factor of 512 to 2. The neutron-coated aperture imager, we've been demonstrating how we can reconstruct images of induced fission and fission chain reaction neutrons. With Creeper, we're using the coincidence logic to measure proton recoil energy instead of trying to directly measure energy deposition. By applying frequency domain multiplexing, we should be able to, what we're shooting for is to multiplex 16 detectors to a single digitizer channel, so that we should be able to do an experiment with 256 detectors with just one desktop 16-channel digitizer. Finally, we've also been working with Struck Innovative Systems to implement event rejection based on particle ID on their onboard FPGA. So the idea is in experiments where people are only interested in neutrons and not interested in neutrons and gamma rays, you can actually suppress the transmission of events that correspond to gamma rays right there on the FPGA, which will bring down your throughput drastically. And so I'll wrap up by showing the pictures of the people who actually do all the work. Jonathan Mueller, who's a postdoc with us, Pete Chapman, who you just met, Mudit Mishra, who has a poster in the back, Kyle Weinfurter also has a poster, and Rob Weldon has one on the Creeper experiments. And I'd like to recognize our laboratory and Duke partners, Eric Brubaker, Jason Newby, Paul Hauslott and Phil Barbeau, and of course Justin Hutchinson for helping making the experiments possible at the Nevada test site. Thank you.
And so obviously you get the most emission from the center. At early times, you see this very intense UV radiation, which could cause that radiative heating of the surrounding gas. And